So hey, I've got a very niche topic for you, but it's one I really find interesting. And this process starts really out of curiosity, something that I'm working with on my astrophotography, on my gear or processing or whatever it may be. And then using data that already exists or is readily available to create, and then asking what that data is actually telling me and how an astrophotography system behaves over time. My name is Doug, and this is Astro AF. So the goal here is not to chase perfect numbers or over-optimize my workflow or anything like that. The goal is to turn some intuition that I may have into something measurable. So changes that I may want to make can be made with confidence and based on data and proof rather than my own perception or feel or what have you. That helps improve the overall imaging experience and things become more reliable. So in this video, we're going to go ahead and take a look at the focus being polar alignment and on my pier-mounted system, and specifically the goal is to understand how well the mount holds polar alignment from session to session, and which parts of the system are doing most of the work when alignment corrections are required. So anyway, we'll walk through how data already is logged by NINA, can it be used to answer those questions, how that data was extracted and visualized, and how the results changed where mechanical improvements are being prioritized. You could certainly apply this approach to other aspects of your astrophotography process, image data, guiding logs, whatever you happen to come up with that you may have questions with. So I think what I want to do is I'm going to transition over to a screen share. It makes the most sense, and I can show you and illustrate, what I've actually put together here. And I'm going to share this also, so you'll be able to find the script that I've written, and that'll be on GitHub, I think is what I've decided where I'm going to put that. I probably do a blog post around this as well. So if I get that done, then those links will be in the description. And then whatever else, if you have questions or comments about what I'm going to be talking about and showing here, then certainly down in the comments or hit me up over on my Discord, and we can definitely do that. Discord link is down in the description as well. So let's shift over and we'll take a look at what I'm up to here. All right, so over here in NINA, in the 3-point polar alignment plugin configuration, there's only one thing that you need to do, and that's here on log polar alignment error adjustments. Just turn that on. That's all there is. You're done. And from that point on, every time that you do a polar alignment, it's going to log that for you. So the next thing we want to do is go ahead and locate where those log files are, and generally, unless you've changed it, those are going to be located in the NINA logs, and for me, that's located in my documents. And if I go over to the NINA logs and documents and into polar alignment, then I can find all the polar alignment logs that I've been generating. I started logging about mid-January, as you can see, and started accumulating data from this that then I could use. I wanted to automate this process, so I wrote a script for that. But first, before we get into the script, let's take a look at the log files. So if we go over to look at what we actually get, we get structured data out of this log. So the part that I have highlighted here is actually, is JSON structured data. Before that, we have the date timestamp and a separator. Okay, so we're going to need to deal with those because what we're while we do want that date timestamp, our structured data is what we're really interested in here, and we need to make sure we parse that out correctly. So anyway, that's where the TPA log files are stored, and where you can get at them and what they contain. So most users never look at these files directly, but they contain far more information than typically used during a single alignment session, and then it can become really useful to analyze this data and see if there's anything to be learned from it. Initially, I was doing manual logging, and my original idea was to just manually log the starting and ending polar alignment error in a spreadsheet. And while that approach, it worked sort of briefly, it doesn't scale, and it introduces bias and inconsistency over time. I had to like take a screenshot at the beginning of TPPA, and then another one at the end so that I had the beginning and ending. Then I discovered that I actually do get to see the beginning offsets or errors, in the last screen, because it shows you that in small text at the very bottom. So anyway, I was managing these screenshots to grab the data out of and type it in by hand and everything. So anyway, I started looking at the plugin and I discovered, hey, there's logging here. And it made more sense to rely on the logging data itself and automate the extraction process, because that's a lazy thing. And that's the kind of stuff that I like. So anyway, let's take a look at this Python script. I'll give you a quick overview. So I wrote this Python script and it performs a focused set of tasks. It parses each TPPA log file. It extracts two meaningful states per session, the initial alignment state and the final solve state. It converts all the values from degrees to arc seconds, because that's the way I wanted to look at it. And it records the number of adjustments or plate solve steps that were required in order to get the count, which for me represents a level of effort that it took in order to get to an acceptable alignment for that session. And then it outputs a clean CSV summary file. So I'm trying to avoid complexity. The intent is repeatability and accuracy. I want to make it easy. Things like doing the manual logging of the polar alignment wasn't easy. I ended up not doing it, and then I don't get any benefit from that. But doing it this way, I get a lot of this. 95% of this is automated, and I just have to take a couple steps. I don't have to do it every night. I can accumulate log files and come back in and sit down and do 3 or 4 sessions to get the data and have a look at things. So it's lower pressure. So let's take a look at the script, and I'll walk through, basically what's going on. So it's PA extract pi is the name of the script. And again, I'm going to put this up on GitHub. I'll have a link to that down in the description where you can pick it up. I'll have a README on that too that will explain some of the stuff, basically, the basics on how to run the script and stuff like that. But what we've got the pandas library that we're using, and this helps us get structured data. It turns it into like a 2-dimensional tabular data, and that's what we really want for generating the CSVs. We're going to import the JSON library here because we're dealing with the JSON. We want to do some parsing and pathlib because we're going to import a file. Initially, we go ahead and set up an argument in this section here, and that's basically us passing in the file name. And then once we do that, we set up a new empty array for the records. Those are going to be the records that we extract out of that log file. And then we're going to loop over those records in that file. And so for each one of those, we want to make sure we find the first opening brace, because that's the beginning of our structured data in this particular data format. So this script is written specifically for the TPA output data, log file data. Okay, so it works with that. You'd have to modify it to work with other things depending on what that structure of data in the logs is. So anyway, we're trying to find that first brace. And that's because when we go back and look, this is where our structured data begins, all the way through to the ending brace. So we're going to parse that out as our structured data. And then we're going to continue through. We're going to load that JSON string, and we're going to decode it and continue. Well, that's it in an error if we get an error from that JSON, and then continue if we do get an error. And then we're going to grab that timestamp, and we're going to increment this count. And above here, I have a count variable set to 0. And that's just to initialize the count. And we're going to count each one of these rows as it comes through. And then we append the row to our data. And then we want to do a check here. If our records are less than 2, then we'll raise an error because we need to have at least 2 records so we can have a beginning and ending. We want to go ahead and do this data frame, and this is the Panda library is doing this, and it's creating this data set for us in a tabular format that we're going to use for the CSV. We only want to keep the first and last entries here, so that's going to be what our basis of comparison is for this. I'm not interested in all of the data that's in between the first and last and what it took to get there. I'm interested in the difference or the delta of the last record to the first record to see how much deviation in alignment for the different axes was required. I do a conversion to degrees here to arc seconds. Just basically taking that column, so altitude, azimuth, and total, multiplying it times 3600 to get the arc seconds out of the degrees. So this first row that's in there is, as far as the count is concerned, I assign it a count value of -1. And this is so that I can use that -1 for filtering later, and I'll show you that. The second row actually gets the actual count. So the number of times that we looped through here and found records and the count got incremented, that's our final count number. Could be 8, could be 10, whatever it took. How many plate solves did we have? And then we go ahead and get our columns ordered in this format. So timestamp, count, altitude error, azimuth error, and total error. So that's our column headers basically. And then we define our output folder to the directory output, which the / means here in the same directory, and I'll show you that. And if it doesn't exist, we go ahead and create it. And then we output a CSV file to that with that summary data in it that we grabbed from Panda, that we parsed out of the JSON. And then we create that CSV. Just print the screen that it's been written. So at that point, we actually can go back to so here in our output directory, then we've got the summaries that I've already generated. And then back in this polar alignment, we've got our logs that I've run the script on, all but this last one here. So I'm going to run this script on this last file. I'll show you how to run it. It's really easy. And then that will generate the new output file in the output directory. So we're in the polar alignment directory right now, and I'm going to pull up this PA extract pi. So we're going to issue a Python command to run this Python script, and then we're going to give it the file name, which is this last one here, that we want to go ahead and parse so that we can import it into our spreadsheet for data. So if I run that, that will go through. It's real quick. It creates the polar alignment summary CSV. And so at that time, we can go back to our output directory and we can find that 2.6 summary CSV here. So that's how you run the script. So for each TPPA log file, the script produces a corresponding CSV summary. And then once the CSV is generated, the original TPPA log file is no longer needed. It can be deleted at that point. Your long-term tracking becomes these CSVs. It has the same information in it that the log files did, and that way you can save space on your drive. You don't have to keep these logs forever. So the CSV becomes a permanent record. And in fact, once you import those into your spreadsheet, then you've got that, and you can delete these CSVs as well. So you can keep things tidy. I'm going to make the script available. As I mentioned, it'll be on GitHub. So whoever wants to review it or adapt the approach, you'll find a link down in the description where you can grab the script if you want to mess around with this yourself. So let's go over and take a look at the spreadsheet. So the CSV files are going to be imported into Google Sheet in my case. And I've got this structured into 2 main sections, which we'll have a look at right now. Okay, so I'm going to go ahead and import now. So I'll go to File, and we will import and choose Upload. And I will drag over this new summary that we have. Important to append to the current sheet and not replace it. Import the data. So we get 2 new rows. We've got the -1 count row, and then we had 17 plate solves in this session. And we have our alt, as, and total arc seconds at the end that represent our session beginning and ending. So now, if we go over to the session summary, This section is going to derive a session summary, including the initial altitude and so forth that I mentioned. And so we have our initial offsets and our alt corrections, our PA offsets and final PA for initial and final here, our plate solve count, and we need to apply this filter. This is kind of a quirk. We don't want to see -1. All right, let me get this out of the way. So back up here in our data, then we should just be able to copy and paste. So we get our formulas that drop down, just like that. And so we've got our 2.6 data with our initial offsets for alt and as that came in from the data, and our correction, and then our finals, and then our improvement, and what the percentage of that improvement was. Don't pay attention to the last one here, because this is actually requiring that we need the next session in order to compare that to. But then I have this visualized, so I can pull this chart over into view. Basically what we're doing here, so these counts, these tell us the number in the sessions, so I can just hover over and see what those counts were for those sessions. And then I've got like here, so that's the plate solve count, our initial PA offset, so we can see this here. Our final PA correction, which you'll see right underneath it there in red right there. And then our alt correction. So this was interesting to me. The alt correction correlated nearly exactly to the initial PA offset. And that was surprising. I'll discuss that in just a second. And then the azimuth correction, which is here. And then I also, if you notice, I have some fainter lines here. These are trend lines. So over time, these tell me how we're doing. Are my polar alignments, and is the mount holding polar alignment better from session to session for each one of these different dimensions that we're looking at? And then finally down here. So everything seems to be making an improvement, or it's level, and that's what I'm looking for in this. The separation that we have here allows the raw data to remain untouched over in the TPPA data tab. And then the derived metrics that I've got here in the session summary are where we can take that data and turn it into information, and then this visualization. So this is where in this visualization that this behavior becomes clear. So again, this was a combo chart, and it allowed me to display the different dimensions of the data, like the line plots, and show the initial polar alignment offset and altitude correction, the azimuth correction, the bar plots on the secondary axis show adjustment count. This count provides me with that metric that indicates the level of effort and what it took to get an acceptable final correction. So specifically, this is the number of plate solves it took to complete the alignment. And then the trend lines that I showed you indicate longer term behavior trends, which show how the system is progressing following the changes. So this structure allows a direct comparison between how far off the mount starts, how much correction is required, and which axis contributes most to that correction. So I had initial assumptions on this. So before seeing the data, my expectation was that the azimuth would be the dominant source of error. And that's because of when I'm at the scope and I'm doing the alignment, I felt like azimuth was the hardest to get to polar alignment. But as it turns out, the azimuth adjustment just felt worse mechanically. The azimuth bolts feel less controlled, and intuition was telling me that azimuth was the limiting factor. But what this data really shows is that something completely different here. The altitude correction dominates the total polar alignment correction. Adjustment count correlates much more strongly with the altitude error magnitude. Azimuth error converges quickly and consistently, while altitude error often requires repeated correction passes. So from session to session, polar alignment drift is primarily driven by altitude behavior. That kind of blew me away because I really didn't expect that. So in short, azimuth feels bad, but altitude behaves bad. All right, to kind of sum up on this. So this approach turns polar alignment from a subjective process into an instrumented one. The broader takeaway that I have is it's not the specific chart or script, but there's a mindset behind this. The data already or can exist in many astrophotography workflows and normally easily, like TPPA logs. Making use of that data can provide insight into how a system actually behaves and can guide improvements that meaningfully affect imaging quality and reliability. And in some cases help provide a paradigm shift in thinking that would otherwise be like incarcerate until shown in actual data visualization. This is a very powerful technique for making decisions for corrections and modifications to your astrophotography gear and settings. Where I'm at with this is the altitude bolts are really hard to adjust. And, I've had it in my mind for a long time, but I didn't really think anything of it. But what I think is happening is that I'm getting like a thread binding with the altitude bolts against the altitude boss on the mount. And that thread binding is like releasing energy over time, between sessions and coming out of alignment. And this is really simple. All I really need to do here is to lubricate the altitude bolts. I probably need to add lubrication to the end of the bolts where they interact with the altitude boss. And then I need to lubricate the threads so they don't bind. And obviously when I make these adjustments, I can feel it. It's really hard to get an initial movement, and it feels like the two altitude bolts are competing with one another rather than, working back and forth on the push-pull. So I think this is as simple as lubrication in order to see an improvement in the altitude. And so I'm going to do that. I'm going to make a note. I might modify the visualization with a notes column. And then if I make a change, identify that in the graph with the bar or something like that that says that a change was made here. And then I can compare from that point on if that change made a difference or not. In this case, what began as curiosity over how a mount aligns and holds between sessions became a clearer picture to me anyway of how the mount actually holds alignment over time. So I like this whole process. I hope you liked it too, and I find it really interesting. And that whole paradigm shift that I had that led me to understand better what the problem area actually is versus what I thought it was. That's going to be an opportunity for improvement that ends up, not being what I think will be a big deal. But I wouldn't have identified it otherwise because my thinking was incorrect out of the scope by basing it off of my own intuition and feel, which was incorrect in this case. Oftentimes it's on the money, but in this case I was wrong. Visualizing this data and analyzing it in this way allowed me to see that and correct, the way that I was thinking about it, with evidence. So anyway, I think that's pretty cool. I hope you do too. And again, you can grab this script if you think you'd have fun doing it and checking it out. I certainly think you could do this if you have if you're on a pier or if you're on a tripod. It's probably best if you leave set up on a tripod, so you can measure night to night without having the differences in setup. If you're pulling stuff down, it may not be that meaningful to you. But if you are leaving your rig set up, from night to night, and you want to see how your PA changes and maybe get a better understanding of what's changing the most for you, that give you an opportunity to address things and make it better so polar alignment is easier and holds up better over time. So again, anyway, I hope you enjoyed that. I really appreciate you, and thank you so much for watching. My name is Doug. This is AstroAF, and I'll see you in the next video.